Nerve signals. How do they actually work? A nerve signal is a fairly complex procedure that is basically I want to say powered by the movement of ions across the membrane of a neuron. So what we're going to do is we're going to draw a membrane, just like we did before. And we'll leave a little space there for a complex protein molecule that we're going to stick in there. Some tails, and we'll put our bulky protein here. This protein, as we've already seen, is called the sodium-potassium pump. And you'll remember that from before. We used it as an example of an active transport, right? Sodium-potassium pump. And you'll recall that the sodium-potassium pump uses ATP energy so the ATP, sorry about that. Thank you. I'm not used to this side work. Okay, uses ATP energy to change the shape of this protein to allow for the movement of sodium ions, 3 of them, pumped out of the cell, while at the same time, potassium ions, 2 of them, pumped in. Remember that sodium-potassium pump? And it uses energy to do this. This is one of the reasons why our brains consume so much energy. Neurons are constantly consuming ATP to keep this flow of ions working. So what this means is, because of the number of ions transported, there is a very there's an electric gradient across this membrane. This side becomes more positive, and this side becomes relatively negative, right? Now you might wonder, well, if you're pumping potassium in, how can it be negative? Well, you're pumping in less plus than you're taking out. So that's kind of like a net drain of positive charge to the top, right? To the outside of the membrane. So this is the outside of the neuron, and this is the inside of the neuron. Okay, so now the end result of this pumping is that a neuron let me draw that axon a little wider. With its axon stretching out, I'll just draw it a little larger to exaggerate. What this means is there's an overall positive charge outside of the axon. And relative to that, the inside is more negative. So this voltage gradient is created by the sodium-potassium pump using energy. And the cells are constantly running these pumps and maintaining this. And we know that we can actually administer a kind of a toxin or a poison that can interfere with the action of this particular sodium-potassium pump. And when we do this, this voltage gradient disappears. So we know that this voltage gradient is produced by the action of the sodium-potassium pump in the neurons. And it has a number. So you'll recall from your grade 9 and 10 that what voltage actually means is essentially it's a hill of charge. Right? That's what a voltage is. It's a hill of charge. We can understand the concept of a hill of dirt. If you take dirt, if this was the original level of the ground, and you dug this hole on this side and piled it up over here, then what you've created is a hill. And in other words, it's a gradient of dirt, or a gradient of height, right? A height gradient, by piling the dirt in one spot, taking it from another. And we know that things will roll up and down, well, mostly down, hills. Put a ball at the top, it'll roll down all the time. Likewise, if we pile up charge at the top by taking it away from the bottom, we can make a hill out of voltage. It's the same concept. And of course, then what that means is charged objects will roll down the hill, just like a ball would roll down the gradient of height. So a gradient causes the movement of things. And we know, of course, these concentration gradients want to influence the movement of charged ions. So in this particular situation, because the membrane is constantly working, it's creating the gradient, but Mother Nature wants the gradient to even out. Given the chance, those ions will flow back through the membrane to the opposite sides to go back to make that gradient even. But they're prevented from doing so because there needs to be specific channels for them. Now with heights, we can talk about how many meters a height is. Right? We can measure the height of a hill by meters. And we can measure, actually, it's not even meters, but we can also measure the steepness of the hill. The steepness of the hill tells us whether or not it's a sort of a fast rolling hill or a small rolling hill, right? Well, the steepness of a hill of charge is called voltage. That's what voltage means. High voltage means you've created a very strong difference between plus and minus. You've made a very steep hill, and it will really push things a lot. I don't understand why this thing is acting up. Okay. It will push things a lot. So what we measure the steepness in volts. Of course, we use millivolts for relatively small gradients or hills, just like we can use millimeters and things like that. And so we measure the biological gradient across this membrane to be about minus 70 millivolts. That's what we call the resting potential. Another word for voltage is potential, because it describes the potential of ions to move, right? Just like you could say a hill represents the potential of a ball to roll. So the resting potential is about minus 70 millivolts. It's not a whole lot of voltage, but it's enough for a cell, yeah. Yeah, so the sodium-potassium pump achieves this, right? It achieves this resting potential by forcing those ions, those 3 sodiums out and 2 potassiums in constantly, and it creates a difference between the inside and the outside, and the value of that difference is about minus 70 millivolts. All right. So now, that's the sort of resting state of a cell, a neuron. They're all sitting there with this voltage across their membrane. When you disturb the cell in some way, and this disturbance could be a physical disturbance, like a pressure or a push, it could be a chemical concentration difference that causes this disturbance. In other words, if you do something that affects the membrane of the cell in some way, what it will do is it will change the way the membrane is permeable to sodium and potassium. And that change will cause the voltage in that spot to change as well. And that's what starts the signal. So the signal is a rapidly changing membrane potential that sort of bumps its way like a domino effect down along the membrane. Okay, let's talk about how this works sort of in numbers. All right. Now, if I go back to my picture, remember this picture I drew of the membrane way up at the start? I'm going to add to that picture. So I'm going to draw that picture again, just so we have something to visualize. Here's my membrane. We'll leave room for our sodium-potassium pump there. And then we're going to put some other guys in here. there's our sodium-potassium pump. So I'm just going to write N, A, K, pump. And so we'll just remind ourselves of what it's doing. It's bringing 3 sodiums out, 2 potassiums in. All right, now in red, I'm going to draw this guy. And he's going to be what we call a sodium channel. He's another protein that specifically can open and close and allow for sodium to move through. Sodium channel. And then another guy over here in purple is going to be a potassium channel. So remember, membranes have all kinds of protein gates, right? That can open and close and let things in and out. So these are particular gates that will open and close and allow for the movement of sodium and potassium. Okay. So, we're going to keep referring to this picture, and we're going to sort of write a step-by-step sort of bullet form process of what's going on. And I'll just pause and give you a chance to catch up to me. So bullet number 1, the first sort of thing that happens is there's a stimulus. The stimulus could be chemical, could be a concentration variation, it could be electrical, it could be a voltage stimulus, in other words, charged ions in different concentrations. It even could be a physical stimulus, where there's a physical pushing or pulling on the membrane that deforms it. But no matter what essentially happens is the membrane is disturbed. So what we want to say here is that the stimulus disturbs the membrane in some way. And when you disturb a membrane, you change it. You change its function. Remember what membranes are. They're very fluid, gushy, sloppy organizations of molecules that hold themselves together by their hydrophilic and hydrophobic nature, right? And to have these protein gates inside. So the stimulus will disturb the membrane in such a way, and it will cause one of these gates. And we're going to talk about the sodium channel, which is normally closed. Obviously, these gates are closed because if they were open, the sodium-potassium pump would be pushing the sodium out, and then it would flow back through, and you wouldn't achieve anything. So these gates are typically closed unless something disturbs the membrane. So the first thing that happens is you get the disturbance opens sodium channels. Now, I'm simplifying this a little bit because it turns out there's actually 2 types of sodium gate. There's an activation gate and an inactivation gate, kind of. And so, because there's 2 different types of sodium channels, we're going to sort of compress their action into one action to keep it simpler. The sodium channel opens, and what begins to happen is we get a trickle effect. A trickle of sodium ions back into the cell. So go back to the picture, right? And what will happen is sodium that's been pumped up to the top area will begin to trickle down through the sodium channel back into the cell. Now, because the activation gates and inactivation gates open at different rates, at first it would be a slow trickle, but it would slowly build up. And as it builds up, that causes the cell potential, the gradient, to slowly drop. Okay, so this causes the resting potential to begin to rise. Now, I'm going to say rise because it's already a negative potential. We're describing the inside compared to the outside. The inside is more negative than the outside. That's what that means. So if you let sodium trickle in, then the inside will become less and less negative. Think about negative numbers. If you're at negative 12 and you go down to negative 6, that's an increase, right? You're rising. You have to add to that to make it happen. So it begins to rise. So this minus 70 millivolts begins to drop, or to rise up. It goes 70, 69, 68, 67, 66, and it begins to drop, okay? All right. This is called depolarization. Another way to describe a gradient is to say that something is polarized. If I pile up a whole bunch of dirt in one spot and leave a big hole in the other, I've created a polarized dirt, right? When things are polarized, it means there's clearly two different ends, one with lots and one with none, instead of a nice medium where everything's even. So a membrane is polarized because the sodium-potassium pump is pushing all the positive out. So it's polarized. This is called depolarization because it's the opposite effect. It's reducing that polarized membrane potential. Okay. Now, this sort of has an effect on the depolarization affects more sodium channels. So we've only drawn one in our picture, but there are many, right? We just drew one to show the idea. So affects more sodium channels, causing them to open, which results in a larger influx of sodium. Incoming, right? Of sodium ions, which makes potential change even more quickly. And at some point, it will get to the point where this is like a positive feedback cycle. Negative feedback was when the response caused whatever was happening to diminish. But here, we have a positive feedback, one of the few places in biology where we see positive feedback. The leaking sodium through the channels causes more sodium channels to open, which causes more leaking of sodium, and you get the feedback. So what this does is that creates a very, very sharp change in the action, or in the potential, sorry. And this depolarization hits a certain level where we get what's called an action potential. So this, not really, I was going to say cascading, but that's not really what it is. It's more of a positive feedback. Positive feedback loop results in, I'm going to put the word extreme just to differentiate between the slow trickle and this extreme depolarization, where the voltage actually flips, where the voltage reverses in that section of the membrane. Okay? This is called an action potential. Yeah, just a minute. All right, so we're going to draw a little picture of our neuron again. I'm sorry, what? voltage reverses actually in the section of the membrane. Okay, so here's our area of the membrane. I'm going to sort of draw it down near this end. Remember, we've got positive on the outside, right? And negative on the inside. But in this little section, I've left a space there on purpose, right there, in that space. Because of the disturbance, the potential has reversed. The potential has reversed. This reversal happens to be, if I just draw a little arrow here, this is the action potential. And what happens is, because of that positive feedback where the sodium is flowing in, it doesn't just drop to zero from -70 to 0. It overshoots and it flips completely. And it's about, I'm going to say, +30. So this has about +30 millivolts, which is a significant change, right? If you go from -70 to +30, that's a 100 millivolt difference. And because you crossed over the 0, you reverse the polarity. Okay. This reversal of polarity the action potential change causes nearby sodium channels to open. So the sodium channels respond to voltage changes. They're called voltage gates. They can respond to physical changes, like physical pressure changes, usually in the nerve ending, wherever the nerve sort of begins. The first neuron in the chain will have a specialized sort of body that allows it to sense different things. So some are sensitive to pressure, some are sensitive to heat, some are sensitive to chemical changes, and so on. But once we get down here on the axon, essentially the sodium channels in this axon are sensitive to voltage. So with the rapidly changing voltage here, the ones nearby are also being affected. That means that if you go one step over and you look at what's happening sort of in this region, sodium channels are beginning to open, and the sodium is beginning to depolarize the membrane there. So it's like a domino effect. All right? This depolarizes the membrane. This. The membrane ahead of the action potential. So now it's the same process, sodium channels opening, but it's sort of spurred on by the rapid voltage change in behind it, the red action potential. And that means that the very next part of the membrane is going to also flip and reverse. So now we have another picture. I'm just going to do one side. That's all that matters. Here's my reversed. Now the part over here is reversing, and maybe it's even reversing a little bit more over here. Whoops. Because of the open channels. So the action potential is sort of spreading its way down, right? Like this. But then something else is going to happen. As the action potential spreads itself this way along the neuron, the ones in behind are going to change as well. As they get further and further away, right? If the action potential here is moving further away, afterwards, so the next step is that as the action potential passes, the potassium gates can open up. And when the potassium gates open up, this has the effect of sort of resetting everything back to normal. Yeah, okay. So potassium gates begin to open. Potassium channels. As the potassium then leaves the cell, so potassium rushes out of the cell. So the sodium rushed in when the sodium channels open. Potassium rushes out because if you look at my little red depolarization here, in the region of the depolarization, the outside is negative. So I'm looking right here at this point. Once this action potential moves down here like a domino, here the potassium channels open and cause positive potassium to start moving out towards the negative, which flips it back, right? The positive charge goes out and replaces it. So what you have is you have now potassium rushes out and repolarizes the membrane. So the picture would look like this. Here's our neuron. Here's our action potential. These are the repolarized sections. And then in red, we have the action potential or the depolarization still working its way down. So essentially, it's a domino effect where the little action potential, the little depolarization in red is shooting along the axon this way. And it's basically just like dominoes. So to kind of put it all in perspective, a stimulus causes the opening of sodium channels, which causes a slight depolarization. That minus 70 begins to change, 65, 60. And then it gets to a certain point. Usually once it gets to about, I didn't mention this before, but when it gets to about minus 50 millivolts, that's sometimes called the threshold potential. That's kind of like when it goes from a slow trickle to a large influx. That's the point where a lot of sodium channels would start opening, and then you get this massive flip, which is the depolarization. So it's a slow trickle at first. 70, 65, 60, 65. At 50, lots of sodium channels are now open, and it shoots up to plus 30. That's the action potential. That's the red depolarization that we're talking about. Then, that shooting up and causing the membrane to reverse its polarity causes more sodium channels in front of it to open, and the whole process starts again. And it just dominoes its way down. But in behind it, it's also restoring itself by the opening of potassium channels, which allow potassium to flow back and put it back, see the blue part here, to put it back the way it was, the restoring of the potential. And essentially, you get this ripple effect, boom, like a domino shooting down this axon. Okay, so I'm gonna wrap this up with a sort of a little graph here. And on this graph, we're going to see the membrane potential on one side. And then on the bottom is basically time going by. And so what we notice is we have a cell that starts off right here at its resting potential. That's the potential. There's a slight trickle effect as the sodium channels begin to open when the stimulus is applied. And then you reach a certain point where it shoots up. And then drops back down, and typically it actually drops slightly lower and then quickly recovers to the resting potential. If you've ever had experience with damming water as a kid, building little dams and things, if you open gates and open things and allow ions to flow, what will often happen is instead of just flowing to equal, they will slosh all to one side and then slow and sort of slosh back and forth a little bit, right? So you end up with more water on one side and then it flushes to the other side and then it comes back. There's a little bit of a back and forth. And so what happens here is the same thing. Those ions sloshing back through, those potassium ions, actually bring the voltage actually a little past the resting. But if I put on here with a dashed line, this sort of right here, that's the resting potential. And that would be the minus 70 or so millivolts. So we'll put minus 70 millivolts there. The action potential itself rises up to about plus 30. So 30 millivolts plus. So this part, this rapid, this is the action potential, this high hump on the graph here, right there. And that represents that extreme depolarization that slides down. So you can see how on this graph, just one second, I'll get to your question in a second, this is where the stimulus is applied, here. The stimulus happens here, which causes the sodium channels to open and begin the leaking, which drops this. But when you get to this level right here, sort of right about there, I wanted that to be black. That's when you get this massive sort of shooting up, and that's about the minus 50 millivolts. And that's what we call the threshold potential, remember? The threshold is sort of like the border. A threshold in real life is in a doorway, right? You know what the threshold is for? You know, when you get married, the old tradition of carrying the wife over the threshold. Well, in the olden days, the threshold, your floor was made of straw. It was a dirt floor, so we often put straw on there so it wouldn't get muddy. And straw was called thresh. And if you had your doorway just kind of open, the straw would keep getting kicked out of the door every time you walked out. So they put a little board there to hold the thresh in the house, and it was called the threshold. So that's what a threshold is. It's sort of the border that separates the inside from the outside. It kind of like this holds the thresh from moving. So the threshold is often what we use as an English word to describe the sort of the upper level of something. It's the level you have to cross. So the threshold potential means if you get to that point as it's leaking out, it will cause a very sudden action potential. Question. So the question was, does it ever get lower than 70? If you look right here, you'll see a little blip that goes down slightly more. And that's because there's an overshoot effect. As those ions are rushing through there, they actually rush through a little bit more than the 70 millivolt threshold. And so therefore there's a little blip, but the sodium-potassium pump is still working this whole time, right? So it very quickly reestablishes that equilibrium at 70. Yeah. Not that I'm aware of. Sometimes it's called hyperpolarization, where you go a little bit past where you're supposed to go. I've heard that used. But essentially, it just means it's an overshoot. You're overshooting your target of 70 by a slight amount, until all the ions kind of settle a little bit, and then the sodium-potassium pump maintains it again. So we'll cut this video here, and then there's a couple of YouTube videos that will show some animations of this that are quite good. This is one I have here. I just found it. I haven't previewed it, but it might be worth watching. So if you're just watching this online, you can get the link and go to that link on YouTube and check out this video. Do the same